Okay, now we're gonna be talking about the round robin, okay, abbreviated as RR. The idea behind the round robin is assigning what we call time quantum or time slice for every process, okay? And this assignment goes on and on and on until processes are done execution. The quantum here is amount of time to be assigned. So let's say if the process has a length of 10 and the quantum is 2, so this process will take that quantum 5 times. 2, and then 2, and then 2, and then 2, and then 2, okay? If the process has a burst of 3, then it will be assigned 1 quantum, full quantum, which is 2, and then just 1 time unit. It will never be assigned another full quantum because it's just 3. If you assign a 1 full quantum, then you're wasting a CPU cycles, okay? If the quantum is huge, then this round robin will work as a first in, first out. If the quantum is very small, then, the performance here is going to be very, very low because of the context switches, okay? So let's look at this example. Okay, again, there is no arrival times. I will solve another one with arrival times, but here the quantum is 4, as you can see. All right, so P1 has a burst of 24. Here it is. So P1 will take the first quantum, 4. So the remaining here is going to be 20. And then P2 will be assigned another quantum. What is the burst of P2? 3. What is the quantum? 4. So P2 will just be assigned 3, and P2 is done execution. How about P3? P3 is also 3 with a burst of 3. So it will be assigned from 7 to 10, 3, and this is done execution. And then P1 will be assigned another quantum, so 16. And then another quantum, so it's going to be 12. That's the remaining time. Another quantum, that would be an 8. And then another quantum, that would be a 4. And then the last quantum, that would be a 0. Here is how the round robin works. Okay, let's solve another problem. Here. I'm sorry, some people are very annoyed because I don't know how to write a rectangle using this. So here it is, okay. So we have here P1, P2, P3, P4, okay. We have here arrival time, and we have a burst. So P1, let's say it arrives at time 5. The burst here, let's give it 10 as an example. P2 will arrive at time 7. P3 will arrive at time 11. P4 will arrive at time 18, okay? This has a burst of 10. This has a burst of, let's say, 5. This has a burst of 6. This has a burst of, let's say, 7 or whatever, okay? And here is the time, starting from 0. So the very first arrival, as you can see, is at time 5. So from 0 to 5, the CPU is idle, right? And then at time 5, I forgot to tell you the quantum here is, let's say, 3, okay? So this is the round robin. The quantum is 3. So the very first one will take a quantum from 5 to 8. This is P1. Remaining time equal 7. 7. Okay, remaining time is 7 here. Then P2. P2 has a burst of 5. Why am I doing P2? Because the arrival time is 7. And now it is 8. So P2 is already there. So P2 will merge into the turn. So now P2 is going to be from 8 to 11. And the remaining time equals 2. Why 2? It was 5. And it took a whole burst of 3. So the remaining time is 2. At time 11, I have an arrival, P3, do you see? Here, there is an arrival. So the arrival here is going to be, it will take a whole burst, 16, all right? So 11 to 14, that would be the P3, and the remaining time is 3. At time 14, you have P1, so P1 will take another burst from 14 to 17, another quantum. So P1 will have a remaining time of 4, okay? Remaining time of 4. Now, the one that comes next is, that's a P2. I forgot to write it here, right? P2 is going to be from 17 to 19 because that's the remaining time. P2 is done. If you imagine the queue now, okay, the queue, it had P2 is done, okay, and you have P1 here. You have P3 here, and the new arrival is P4, which has been there in the middle of here. So this is P4. All right. So you can actually start P3, then P1, then P4. That's correct. Or you can also assume that the newcomer comes here. So you're going to be having P4, then P3, then P1. Which one is correct? It doesn't matter. Okay? Both are fine. All right? Just in the exam, you need to kind of draw the queue to show me how you sorted that out. So the idea here is you can adopt this one or that one, okay? This one based on what? Based on first come, first serve, okay? So P4 comes at the end. So in this case, I'm going to be doing P1 and then P3 and then, P3 and then a P1 and then P4. Or you can have it here as the least recently used process. So you can have P4, P3, P1. Anyone you want to adopt, that's fine. In class, I actually did this, okay? So I'll continue with this. So now P4 just arrived with 7. So I'm going to be giving it 17 to 22. That's P4. And the remaining time here is going to be a 4. Okay? Then I'll go to the P3. It will be assigned 3, so 22 to 25, that's gonna be P3 done, because the remaining time is 3. Comes after that is P1, from 25 to 28. Okay, the remaining time here is going to be a 1, right? Why? Because the remaining time here was 4. After this, we have the P4, which will take from 28 to 31. Okay, that's a P4, and the P4 is going to be a remaining time of 1. See, who finished now? P2 is done, P3 is done, the remaining is P1 and P4. So now give one quantum for P1 here, and then give another quantum for P4. Here it is. So if you want to get the waiting time of P1, a response time of P1, waiting time of P2, response time of P2, waiting time of P3, and the response time of P3. Same for the 4s, okay, here. Waiting time of P4, response time of P4. Look at this. Again, the equation is finish minus arrive minus burst, right? For the waiting. So the waiting time of P1, when did P1 finish? Look, all the way to 32. So this is going to be 32. When did it arrive? Look at P1. Arrived at time 5. What is the burst? 10. Right? So this would give you 17. Huge waiting time. So can you imagine that the burst is 10 and the waiting is 17? Almost double of the burst. Do you see? Why this is happening? Because the round robin doesn't really care about the waiting time. It cares about response time. Now, look at the response time of P1, which is start minus arrive. When did P1 start? At time 5. When did it arrive? At time 5. So the response time here is 0. Can you imagine? The waiting is 17. And the remaining, the response time is 0. Look at process number 2. Process 2 finishes at time, let me see, here, 19. Okay? So it finishes at time 19 minus. When did it arrive? Let's see. It arrived at time 7. What is the burst of P2? Let's see. The burst is 5. So this would give you a 7. What is the response time of P2? Let's see. When did it arrive? When did it start? 8. P2 started at time 8. Okay. What is the arrival time? 7. So here's 1. Do you see what I'm saying here? Look at the response time. That's what the roundabout is all about. It gives you an amazing response time. Okay, of course, as I mentioned before, the response time is deceiving. I mean, you can have a very low response time, but a huge waiting time, as you will see, as you actually see in this example. Okay, waiting time P3. Let's see. So when did P3 finish? Look at the graph. Sorry. Here it is, 25. So 25, when did it arrive? 11, and the burst is 6. So you have here 25 minus 11 minus 6. This would give you 14 minus 6, which is 8. Okay, what is the response time of P3? Let's see, when did it first start? P3 started at time 11. And again, the arrival is 11. See, the response time works like magic. You see, 0. That's what it is about the roundabout. It deceives user. It makes them happy, because the response time is very, very low, while the waiting time could be huge. P4. So P4 finished at time 33. So here's 33. It actually arrived at time 18. And the burst is 7. So this is a waiting time of 8, right? Done. Yeah, 8. How about the response time? Let's see. The start of P4 was time 28. Oh, sorry. The start is 19 here. So the start is 19. So the response is 19 minus. The arrival is 18. So do you see here, it is actually 1. Again, now you can get the averages, you can get the turnaround time. Of course, turnaround. Look at the P1 as an example. What is the turnaround of, let's say, P1? It finished at 32, and it arrived at 5. So 32 minus 5, that would give you the turnaround time, which is going to be 27. Okay, because it's the finish minus the arrive. So that's the roundabout. The RR, the round robin. The idea here behind the round robin is the quantum. The quantum is really, really sensitive. How sensitive it is? It's sensitive in a way that if the quantum is huge, you will turn the round robin to work like first come, first serve. Why? Because the length of the quantum is bigger than any burst. So the process will come, execute, and leave. So it's going to work like first come, first serve. That's if the quantum is huge. If the quantum is very low, we will have a huge problem with performance. Why? Because, as you know, between every two processes like this, there is a context switch, the time to change from one process to another. This context switch, if the quantum is too low, it could be comparable to the context switch, which means that the performance of computation is going to be very low. The CPU utilization is very, very low. Okay?